Can you hear me?
Yes,
Yes,
ma'am.
ma'am.
Thank you. We were dealing with a spontaneous process. What are the criteria for the spontaneity? First, we saw if there is release of energy, if there is release of energy, the process is spontaneous. And we saw water, liquid water kept opened will go up, spontaneous process. It evaporates, spontaneous process. In this case, water molecules absorb some amount of energy. So first we said the reactions or the processes where there is release of energy, they are spontaneous. But this is also spontaneous. Here there is absorption of energy, positive. Absorption of energy, still it is spontaneous. Why it is spontaneous? With a positive energy, positive energy means absorbed. With the absorption of energy, it is spontaneous. This is due to randomness or the disorder attained by the system. Here water is the system. In water, in liquid water, molecules are much more organized, ordered as compared to the molecules in the vapor state or in the gaseous state. So solid, liquid, gas, in gaseous state, the molecules are disordered. We say this randomness or disorderness by the term entropy. Entropy, disorderness. When all students sit in the class and if teacher is inside the class, we say order. If the teacher goes out, then the students disordered, randomness increases, disorderness increases. We say entropy of the class is increasing. It is a rule that is in nature. The systems are going, everything is going from an ordered state to a disordered state. From a disordered state to an ordered state, it is very difficult, or some external agency should be there, one teacher should be there. If teacher is not in the class, students move from order to disorder. That is more randomness, more disorderness. That disorderness or that randomness, that is called entropy. Here it is, in liquid water, molecules are much more organized in the ordered state. Solid, it is again ordered. So here disorderness increases, randomness increases. So entropy is increasing. Entropy is having a positive value, a spontaneous process. So the second criterion for spontaneous process is that increase in the entropy. Second law of thermodynamics states that entropy of the universe is increasing. Universe means system plus surroundings. Universe means system plus surroundings. So there, the change in entropy is positive. Entropy is denoted by S. Change in entropy is denoted by delta S. Entropy of the system is increasing, means change is positive. Entropy of the surrounding is increasing, means change is positive. So there is positive change in the system, there is positive change in the surroundings. So entropy of the universe is increasing, it will be having a positive value. Entropy of the universe means entropy of the system and entropy of the surroundings. So entropy of the universe is increasing. We can say delta S total. For these two things, I can write delta S total will have a positive value greater than 0. Delta S total. So the conditions for spontaneity is release of energy, that is enthalpy, and increase in delta S, increase in delta S. So these are the two criteria for this spontaneous process. One is enthalpy, that is release of energy. That should have a minus value and this should have a plus value. There should be release of energy, so minus value there. Here increase in entropy, that delta S should have a positive. So two things are there, enthalpy and entropy. So two things, criteria for spontaneity is based on what? Enthalpy and entropy. Gibbs gave an equation connecting these two, that is enthalpy and entropy. Enthalpy and entropy. He said G is equal to, he defined a new term connecting these two, that is H minus Ts. He said, he gave a letter G, we are calling it as Gibbs free energy or Gibbs, that G. Connecting these two, he gave a new function that we call it as Gibbs free energy. Here, H enthalpy, S entropy at this constant temperature T. So here, delta G is equal to delta H, means connecting these two, a new function is made. So both are connected, not only enthalpy but entropy also. Delta H minus T into first function into derivative of the second and second into the derivative of the first. At constant temperature, when heat is transferred, to make the temperature constant, that means isothermal process. If heat is not transferred, then it is adiabatic process, Q is equal to 0. If heat is not absorbed, Q is equal to 0. If there is transference of heat between the system and surroundings, that means the temperature is maintained at constant temperature. Delta G is equal to, that means constant temperature means delta T becomes 0. So delta G is equal to delta H minus T delta S. Delta G is equal. So a new function is created connecting this enthalpy and entropy, change in enthalpy and change in entropy. So delta G is equal to delta H minus T delta S. Let's see what should be the state of delta G. Should it be, we said delta H should have a negative value, delta S should have a positive value. Then only the process is spontaneous. Connecting these two, we have made a new function called delta G. Now let's see whether what should be the sign. It should be minus or it should be plus. So for the spontaneous process, then we will be talking only in terms of delta G. That time we won't talk about. You don't have to talk about this delta H and delta S. Combining these two, you can talk on this delta G. We said delta H, that should have a negative value, means energy should be released. Delta S should have a positive value, that means more and more randomness, more or more disorder. Now connecting these two, we will be talking only in terms of delta G. Delta G should have positive or negative value for the spontaneous process. For that, okay, I'm writing it as delta G is equal to delta H minus T delta S at constant temperature T. Now, we know that second law of thermodynamics states that entropy of the universe is increasing, means delta S system plus delta S surroundings should have a positive value, that is delta S total. Delta S total. Delta S total is equal to delta S system plus delta S surroundings. Now, delta S change in entropy is given by, delta S is given by delta H, means actually Q reversible by T. Equation is Q reversible by T. I am writing it on the side. Q reversible by T. The mathematical expression for delta S is Q reversible by T. That is delta H upon T. You can write in this format also. Delta H up. If this is system, then this is also system. If this is surroundings, then this is also surroundings. Okay. Delta H at constant temperature. That means isothermal process. In isothermal process, that is, we learned that delta U is equal to Q plus W. Isothermal means this is 0, that is Q plus W, or Q reversible. Q is equal to minus W. You know that W is equal to reversible work. W, that is minus 2.303 nRT log Vf upon Vi. So that minus of 2.303 minus 2.303 nRT log Vf upon Vi. That means here plus delta H, that is Q reversible. Q reversible is 2.303 nRT log Vf upon Vi upon T. So T got cancelled, and you will be getting 2.303 nRT log nr log Vf upon Vi. Vf upon Vi. Let it be there only. Now, my point is delta S is equal to delta H upon T. So, I am going to write it as delta S total. Delta S total is equal to delta S system plus delta S surroundings. Means if this is surroundings, this is also surrounding. If this is system, this is system. So delta S surroundings means delta H surroundings upon T. Delta H surroundings upon T. Now delta H surroundings, in terms of system, you write the amount of heat absorbed by the surrounding is the amount of heat released by the system, or amount of heat released by the surrounding is the amount of heat absorbed by the system. Anyway, total is constant. So delta H surroundings you can write in terms of system, but the sign will be different, changed. So delta S total is equal to delta S system. I'm going to change that surrounding in terms of system. So minus, I'll be putting a minus delta H system upon T. So I converted that surroundings into system, so I changed the sign. All right, multiply all by T, multiply all with this T. So T delta S total is equal to T delta S. Once, okay, T delta S system minus delta H system. Delta H system. And for a spontaneous process, delta S total should be greater than 0. Capital T is always a positive value. Kelvin temperature is always a positive value. For a spontaneous process, delta S total should be having a positive value. So T is again T is positive. So this T delta S will be a positive value. That means greater than 0. So I can write as T delta S system minus delta H system should be having a value greater than 0. So now all are in terms of system. Once all are in terms of system, then you don't have to use that sys. It is understood that is of system. So T delta S minus delta H system should have a value greater than 0. So I'm writing, I'm taking minus sign outside, that is minus delta H minus T delta S is greater than 0. What is delta H minus T delta S? See, delta H minus T delta S, that is delta G. That is minus delta G is greater than 0 or delta G is less than 0. Means delta G should have a negative value. Ultimately, if delta G is having a negative value, then the process is spontaneous. So you can talk in terms of delta H, it should have a negative value. Delta S, it should have a positive value. Instead of telling these two, you can tell only in terms of delta G, a new function, we call it as Gibbs function or Gibbs free energy or available work. So delta G should have a negative value. So that is the condition for spontaneity. Delta G should have a negative value for a spontaneous process. Write one question. Enthalpy and entropy changes for a reaction are enthalpy and entropy changes for a reaction. Enthalpy change delta H. Enthalpy and entropy change for a reactions are for a reaction are 40.6 kilojoules per mole and delta S, that is 108.8 joules per Kelvin per mole. Joules per Kelvin per mole. Here joules per mole or kilojoules per mole. Delta S, there is one per Kelvin also because temperature is in the denominator. So there will be per Kelvin also in that. So looking at that, you can say that whether it is delta S or delta H. Okay. Predict the feasibility of this reaction at 27 degrees Celsius. Predict the feasibility means, is it spontaneous or not? Is it possible or not? Is it feasible or not? Predict the feasibility of the reaction at 27 degrees Celsius means temperature is 27 plus 273, that is 300 Kelvin. So what you have to find out? You have to find out delta G. If delta G is having a negative value, the process is spontaneous. If it is having a positive value, the process is non-spontaneous. So we are using these things, we are going to find out delta G. Delta G is equal to delta H minus T delta S. Delta H, see, one is in joule, one is in kilojoules. So we'll be writing that also in terms of joules. So here 40612 joules per mole minus temperature, that is 300 Kelvin, 300 Kelvin into T delta S, that is 108.8 joules per Kelvin per mole. So Kelvin got cancelled. So here also joules per mole, there also joules per mole. 108.8. And the answer you are getting is 7990 joules per mole. This is plus 7990 joules per mole. See, delta G is having a positive value, so the process is non-spontaneous. The process is non-spontaneous. Okay, once again I am coming to delta G is equal to delta H minus T delta S. Delta G, we said delta G should have a negative value. Delta G is equal to delta H minus T delta S. If delta G is negative, the process is spontaneous. If it is positive, the process is not spontaneous. If delta G is equal to 0, the process is in equilibrium. Equilibrium criteria is removed from your syllabus. Anyway, we will be seeing all those three cases. If delta H is negative and delta S is positive, then what? Delta G is always negative. If delta H is negative, so this is negative quantity. And if delta S is positive, so this is again T, delta S is T is positive, so this is negative quantity, so it will be always spontaneous. It is always spontaneous. So one is negative, one is positive. Suppose this is positive and delta S is negative. Delta S is negative. So this is positive, delta S is negative, means delta G will be having a positive value. So it is always non-spontaneous. 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 If both are negative, if both are negative, if both are negative, I am writing all the chances. If both are negative, that is this is negative and this is positive. If this much portion is negative, that is a favorable condition. But this is positive. This negative and negative positive. This is positive. So if the numerical value of this is higher, then it will be spontaneous. So for the condition is that the temperature should be very low. So at low temperature, it is spontaneous. At a low temperature, it is spontaneous. Now, if both are positive, so this is positive and this is also positive. So positive in negative, negative. So its numerical value, if its numerical value, the quantity is higher, then it is spontaneous. For that, the temperature should be high. So at high temperature, it is spontaneous. At high temperature, it is spontaneous. So with that, we finish this chapter. Next time, moving to equilibrium. Chapter 7, equilibrium. That is the biggest chapter, largest. So, equilibrium. Chapter 7, equilibrium. You see, when water is taken in a closed vessel, hot water is taken in a closed vessel, or simply water is taken in a closed vessel, some of the molecules get converted into the vapor state. As time passes, more and more vapor will be formed. And after some time, some of the vapor molecules will be condensing back to form liquid water. So evaporation is there, condensation is there. In the beginning, rate of evaporation is higher, and that time rate of condensation, first no condensation, as time passes, condensation start. In the beginning, rate of speed of evaporation will be higher, rate of condensation is lower. As time passes, more and more molecules will be getting condensed. So rate of condensation, rate of evaporation getting lesser and lesser speed. At the same time, initially rate of evaporation will be higher, rate of condensation is lower, speed will be lower. As time passes, rate of condensation will also be taking up the speed. So there will be a stage where you feel that no change is visible. The amount of water is there only at some stage. After one stage, you don't feel that it is getting evaporated. At this stage, the rate of evaporation becomes equal to the rate of condensation. The rate of evaporation becomes equal to rate of condensation, then further no change is visible. This is a physical equilibrium. We say an equilibrium is reached. Means no change is visible, but there is evaporation, there is condensation. At this stage also there is evaporation and there is condensation. At this equilibrium, since both the processes are taking place, we say there is movement. There is movement from liquid water to water vapor and water vapor to liquid water. There is movement. Means it is dynamic. This equilibrium is dynamic. This is liquid vapor equilibrium, physical equilibrium. If you take a glass jar and put some iodine granules in that, iodine granules. When you put this iodine granules, this air was very much clear air. As time passes, you see some violet coloration here. This air is getting violet color. That is, it sublimes, and the color is seen. As time passes, the color is getting intense and intense. After some time, you don't feel that any change in color. Means the color, after a particular color, then further increase, further intensity in the color is not observed. That means in the beginning there was the rate of sublimation was high. As time passes, some molecules are getting condensed also to the solid. From solid to gas, then gas to solid, solid to gas, gas to solid, and the rate of sublimation becomes equal to the rate of condensation. Further, no change in the color is visible. So we say an equilibrium is reached. An equilibrium is reached. This is again a physical equilibrium. When you put solid ice in water at 0 degrees Celsius, ice at 0 degrees Celsius, if you are putting in water at 0 degrees Celsius, again an equilibrium. Some solid molecules are getting converted into liquid state. From liquid molecules are getting converted into solid state. This equilibrium, dynamic equilibrium, both are taking place. Solid is changing to liquid, liquid is changing to solid. So these are the examples for physical equilibrium. Once the equilibrium is reached, both the rates, forward process, forward rate and backward rate, both are equal. Further, no change is visible. This is physical equilibrium. Next is chemical equilibrium that we will learn in the next class. Chemical equilibrium, suppose A plus B gives C plus D. AA, BB, CC and DD. A reaction. In the beginning there was no C, 0 plus 0, 0 and 0. After some time you see a little bit of C and D produced. As time passes, the amount of C and D are increasing. And the C and D are reacting together to give A and B. We show this sign, this sign backward. When the rate of forward reaction means at that time C moles of C and D moles of D are produced. As time passes, this backward reactions are also starting. Means in the beginning backward reaction is very less. As time passes, the amount of reactant molecules getting lesser and lesser. The rate of forward reaction when becomes equal to the rate of backward reaction, then we say an equilibrium is reached. We'll see further in the next class. Thank you.
Thank you, ma'am.